Okay, welcome back. So if you remember in the last class we had discussed about the introduction of p-n junction. We have also discussed about the basics of how depletion region is formed, about the built-in potential. I told you how built-in potential is dependent on doping. We had derived the expression for built-in potential, and then I also told you that wide band gap or smaller band gap materials will have different built-in potentials. I told you that doping and depletion width are inversely proportional. So if p side is very highly doped, then depletion will be predominantly on the n side and vice versa. So doping, and that's because the areal charge density has to be conserved. So these are some of the things that we had discussed in the last class. If you recall, also I told you that depletion region that is formed will also sustain a field. There is no field in the neutral region away from depletion. So all these things we have covered in the last class. And please remember that this p-n junction will be the building block for so many devices. So if you want to calibrate any practical device, we want to understand how the blue LEDs are working, which by the way is your white LED now. Then you understand again p-n junction, right? So everything is p-n junction eventually. So today in this lecture we shall first try to establish a relation between depletion width that forms at the junction and the built-in potential. Okay, and we will derive that expression, and that we'll try to solve some numericals if time permits. And then from next class we will perhaps study about p-n junction in non-equilibrium, which means you apply voltage, you apply bias, so current will flow, and that kind of an analysis we will do in the next class probably. Okay, so today we'll start about we'll conclude p-n junction in equilibrium by establishing essentially the relation between built-in potential and the your depletion width. Okay, so let's come to whiteboard now. This is the so let's get in a new page here. I'll tell you again. So if you recall, this is your Fermi level, right, and this is your conduction band, this is your valence band. So I told you that this is your built-in potential q VBI, right, which essentially is kT by q ln of Na Nd by Ni square. This is your doping on the n side, which is Nd. This is doping on the p side, which is Na, and Ni is your intrinsic carrier concentration. So this is the equation we can actually use to find out the built-in potential. I told you the field is existing only in this region, which is your depletion region. Suppose this was your actual junction at x equal to 0. So depletion extends to x equal to Wn on the n side and x equal to minus Wp on the p side. I told you if the and here I am assuming that doping Na and Nd are moderate and are similar. If one side is very highly doped, then the depletion will be only in the other side, okay, in the lightly doped side, if you recall that, okay, because this is your P, this is your N, some depletion forms here, some depletion forms here. This areal density of this is Wn, right? So Wn times the doping that is there, Nd, in this should be equal to the areal density here, that's equal to Wp into Na. That's why it comes, okay, the inverse proportionality, if you recall. Okay, so now if you draw the charge diagram of this, of course, if you draw the charge, then you will see that this is x equal to 0, this is x equal to Wn, this is x equal to minus Wp. So on the n side you have positive charge, plus 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 plus, this is Nd, this value is Nd. On the negative this side you have minus, this value is minus Na, so this is minus Wp, so you have minus minus minus. So the area under this and area under this has to be same. That is what we have done with this. Okay, let's focus on say this region, the depletion on the n side, whose width is Wn, and this is filled up with positively charged ionized impurities, right, this whole thing. So let's focus on that. Okay, so if I focus on that, then I'll draw it in a smaller scale so that we can do the analysis, also do the mathematics at the same time. So this is the thing. Okay, so I told you that this is your say junction x equal to 0. We are going to concentrate on this part, which is x equal to 0 to x equal to Wn. So it's the depletion on the n side. Okay, the field exists in this region, also the field exists in this region also until this region, but we will consider only up to this region. The field exists here. There's no field, also there's no field in the neutral region, which is this, right, this region, there's no field. Okay, the field only exists in the depletion region. So now we have to believe, or we have to understand that in this region we have only Nd plus as the background charge, because mobile electrons have recombined with holes when they were forming the junction. So, only Nd plus is the charge that remains here, which are immobile. Similarly, Na minus remains in this part, but we shall come to that later. But and both Na plus and Nd plus have to balance each other, the areal density I just told you now. So, we will consider we understand that in this area, in this in this block essentially we only have Nd plus. So, now we shall write the Poisson equation. You remember the Poisson equation from your 10 plus 2. Poisson equation does come from Gauss law, and if you recall, it is basically the second derivative of the voltage. This is conduction band, this is valence band, this is Fermi level. You remember that this is electron energy, this entire band diagram is electron energy. So, this electron energy, this whatever I am putting as EF, EV, this is electron energy, actually is your Q times potential energy. Please remember that, okay. And there is a negative sign, of course, because charge is negative electron. So, this is essentially, before I come to Poisson equation, this is essentially energy band diagram for electron energy. The potential will look opposite to that, the potential will look somehow in a mirror image. So, it will look like the potential will essentially look like opposite. So, it will look like this, which means this side is a higher potential. So, suppose this was 0 point, and if I take this reference as the 0 potential, then this potential, there is a potential drop that is changing as a function of x, right. As a function of x, the potential is changing, you see this, but this total potential drop that has happened is actually q VBI that we know, okay, because that is only this. It is just that it is a mirror image, because potential is negative of the electron energy is negative of potential, okay. Anyways, so here we are talking about potential. So, the second derivative of the potential is equal to total charge by epsilon naught epsilon s. Epsilon naught is the dielectric constant of vacuum, which is 8.854 into 10 to the power minus 14 farad per centimeter. This is your the free space dielectric constant, and epsilon s is the dielectric constant of the material. For example, in silicon this is 11.7. Okay. What is the charge? I am talking about only this part, as you recall, I am only talking about between 0 to Wn. The charge in this part is Nd plus, I just told you now. So, I can replace this by Q Nd plus, fine, I can replace that as Q Nd plus. Okay. Now, I have to solve this Poisson equation to essentially get V, but before that I can say that electric field, and that might be a function of x also, there is an electric field in this region. In this region there is a field because there is a slope. There is also electric field here, there is also electric field here, that there is a slope here. So, the electric field is nothing but the negative of the gradient of potential energy, if you recall, right. So, I can plug this here and I can say that it actually is df by dx is equal to minus q Nd plus by epsilon naught epsilon s. Now, you do a derivative or you do an integral equation. What are we trying to find out? We are trying to find out field f of x in this region, Once you find out the field, you can find out the potential. Once you find out the potential, what will happen? You can find out at any point x what is the potential. So, it will also give you many ideas actually, we will come to that. Okay. So, now we have to solve this equation. df by dx is equal to q Nd plus by epsilon naught epsilon s, which means f of x is equal to minus q Nd plus. I can write this as minus q Nd only, because Nd plus and Nd are same. There is 100% ionization, no, epsilon naught epsilon s into dx, right, into dx. So, I can see the field here. So, how will I do that now? So, field will be now equal to minus q Nd epsilon naught epsilon s into x plus some constant, right, into x plus some constant, or I can just say I can just say this is x plus some constant C1. Now, the first boundary condition, if you look here, is that at this point, okay, let me rub a little bit here. This is a Fermi level, for example, this is a conduction band, this is a valence band. I am talking only of this part, right, only of 0 to Wn. At the end of Wn here the field becomes flat, after that there is no field, which means at x equal to Wn your field vanishes because the field exists only here. Okay. So, the first boundary condition is that f at x equal to Wn will become 0. So, in this I will put f equal to Wn. So, it will become minus q n d Wn by epsilon naught epsilon s plus C1 is equal to 0, because at that at x equal to Wn the field has to become 0. So, C1 is equal to q n d epsilon naught epsilon s into Wn. So, I can write this as f of x q n d epsilon naught epsilon x into Wn minus x. Okay, Wn minus x. What does it mean? It means that the field is decreasing linearly. At x equal to 0, the field is maximum, and that value is q n d epsilon naught epsilon s into Wn. This is the maximum value you will have. As you keep increasing x, this quantity will reduce, your field will reduce. Eventually, at x equal to Wn, your field will become 0. So, field is decreasing linearly as x is increasing, which means if I plot field versus x, then at Wn the field becomes 0, at x equal to 0 the field is highest. So, it will become like that, right, the field will become like that. Except that there is a small a sign, there has been an error, I have put an error on the sign, but that is okay. I mean the magnitude is all the same. Actually, you know, the Poisson equation while solving the Poisson equation, if you look here, there should be a negative sign at the beginning actually, so that negative will cancel out, but that the negative sign will actually not matter, the magnitude is all the same. Okay, the magnitude is all the same. So, this is your essentially the maximum field that you will get. Okay, and the field will decrease linearly as you approach x equal to Wn. So, this is your at the edge of the depletion, your field will become actually will vanish. Okay, it will vanish. So, similarly, I can do the same exercise for the p side. If you recall, this is EF, this is this. I told you that I had only taken care of this is x equal to 0 and this is the depletion edge here. I only took this part, this and the n side, but I can also take, you know, this is minus Wn Wp. So, I can also take this part on the p side. I can solve the same thing and I will get again a field profile that will look like field. So, this is x equal to 0, this is x equal to Wn. So, I told you the field, you know, is maximum here, it reduces to 0 here, this is x equal to Wn. Okay, it linearly decreases to 0. Similarly, on the p side minus Wp, it will basically start from here, the same value will be here and it will basically reduce to 0 here. Okay. So, this peak value, I told you that peak value of field is q from the previous solution Wn by epsilon x is the same if you get from this side also, from if you solve the p side you also get the same value, which will be like q na Wp epsilon naught epsilon s. If you actually, you know, this is the same essentially, the peak, this is the peak field and this is in volt per centimeter. Of course, you can see that you can cancel out q epsilon and all. What will remain here is ndwn is nawp, which is basically the charge neutrality. I have already told you, it basically gives you the same charge neutrality equation, that the areal charge density on this side and this side has to be same. Okay. So, if you recall, again I will rub it here, let's make it this is a Fermi level here, this is a conduction band, this is a valence band. No, actually I have shifted the diagram, so let me again draw it again here. This is a Fermi level, okay, and then this is your conduction band, your valence band, this is your x equal to 0 point, this is your n side, this is your p side. I told you that an electron will roll on this side, so it will go this side. So, the field is in the negative x direction. So, field will be negative x direction. So, the field is not exactly, this is the value of the field by the way, but because field is negative x direction, the field will, you know, essentially look, this is x equal to 0, I am plotting the field here, okay, this is x equal to Wn, this is x equal to minus Wp, this is the maximum field and the field will look actually like this. I mean, instead of positive it is basically negative, everything else is same, the value and everything is same, the field is actually in the negative side, and the reason this is actually negative, but the reason I got it positive as I mentioned is because I missed out a negative sign here in the Poisson equation here. So, that negative sign actually doesn't change anything except the direction. Okay. So basically what's happening is that the field is essentially in your negative direction, so that's why I'm giving it as negative here, but the magnitude and the values, that the way it's decreasing and all, everything is the same. Okay, just an extra negative sign that I had missed out. So this is your field on both sides, and it's linearly decreasing from the x equal to 0 point to this side, and x equal to 0 to this side, right. So essentially at this midpoint the field is maximum, the field decreases gradually in linear way and it becomes 0 here, the field decreases gradually linear way and it becomes decrease here. Okay. Now if you recall the expression for field, okay, if you recall the expression for field, now I'll put the correct expression. F of x is equal to q n d epsilon naught epsilon s x minus w n. This is the true field expression. Now this is actually minus dvx by dx. So I'll write down the I can solve it again now. So it will be v of x will be equal to q n d epsilon naught epsilon s, negative sign is there, so I'll make it w n minus x dx. So now I can solve it. There will be limit. What's happening is that I told you the potential goes like this, so this is your x equal to 0 point, this is your x equal to w n point, this is your x equal to minus w p point, the potential is changing, and your net potential drop of course has to be your built in potential q v b I, which we have already derived. So you see your this part is your depletion on the n side, this part is a depletion on the p side. So this is the potential drop that is happening on the p side, and this is the potential drop that is happening on the n side, remember. So the total of the potential drop will be the built in potential. So the potential that is dropping on the p side, I will say this is Vp, this potential drop, and the potential that is dropping on the n side with respect to the x equal to 0 point, this I will say as Vn. So this total, this potential drop on this side and potential drop on this side will add up to the total built in potential. Okay, will add up to total built in potential. Okay. So now this while you solve, you can put that limit that I am integrating from x equal to minus wp to I am integrating to this point. Then on the n side I am integrating from x equal to 0 to x equal to wn. The unknown quantities will be Vp and Vn because that is the total potential drop that I am having. But eventually when you do the simplify the math, and everything will be uploaded as notes, so there is no point. But once you do that, you will see that the potential that you are dropping on the p side Vp is actually q n a wp square, wp is the depletion here, by 2 epsilon naught epsilon s, and the potential that you are dropping on the n side is q n d w n square, this is the distance x square, by 2 epsilon naught epsilon p. So these are the potential that is dropping on either side of the depletion, and the total summation of these two, if you sum this up to both of them, then that should give you q v b I. So that is the potential that is dropping across each of the side of the depletion region. Okay, good. So now what should we do now? So now we have to I told you we have to establish a relation between the total depletion width and built in potential. Okay, total depletion width and built in potential, we need to establish a relation. Till now we have gotten the built in potential on both sides, right, on either of the side. And how did you get that? We got that by solving this equation. We solve this equation, you can actually you see this is an x here, so it will be x square term, and then I told you can set the limit from x equal to minus wp to x equal to 0. Okay, and that will give you the total voltage drop Vp. Similarly you will get from here to there, you can set the limits here. So for if you do it for the n side, it will be from 0 to wn, you can exactly calculate, that is your Vn, you will get this value. For p type you will get this value, and so you add those up and you will get qvbi. Now so I will write it as qvbi is equal to q n d wn square by 2 epsilon naught epsilon s plus q n a w p square by 2 epsilon naught epsilon s. Okay. Now you also recall that w is equal to wn plus wp because that is the total depletion width. You also recall that wn times nd will be equal to wp times na, that the real density on both sides is same. So here I can say that Wn is actually equal to Wp into Na by Nd. From here I can say that total depletion width is equal to Wn, which is Wp Na by Nd plus 1. So I can say W is equal to Wp Na plus Nd by Nd. So I can say Wp is equal to W into total depletion width into Nd, Na plus Nd. Similarly, I can say Wn is equal to W, the total depletion width, into Na plus Nd. So I can put this value and I can put this value, both of them, into this expression. Okay, I can put them into that expression. What will happen then? I am substituting for Wn as a function of W, and these are doping, of course. Similarly, I am substituting the value of Wp and Wn as a function of W. Okay, if I do that, then on the left hand side I have built-in voltage. On the right hand side I have, of course, I have doping Na, Nd and all epsilon, but there is no Wp and Wn. Everything is expressed in terms of W. Then I can express a relation. If you simplify it out, this is basically mathematical simplification, you will get an expression for W, and that will look like 2 epsilon naught epsilon s by q Vbi 1 by Na plus 1 by Nd, the whole thing of the square root, and this is in nanometer or centimeter, whatever. So this is your depletion width, the total, and this you get from simplifying the above expression. Okay, this is your total depletion width. Let me draw a p-n junction again. This is your Fermi level, this is your conduction band, this is your valence band. Your this depletion, your this built-in voltage Q Vbi, which is this, which is your this, is connected to the depletion. The depletion is this, right? Is connected to depletion by this relation. So if you know the doping, say one side doping is 10 to the power 17, the other side doping is 10 to the power 16. You know this doping, you plug in the value. Epsilon naught, epsilon s for silicon is 11.7, or the material that is given you will find out. Q is the charge of electron. Built-in potential is found out by kT by q, ln of Na Nd by Ni square. Right? Once you know the doping, of course you can find out the built-in potential. Then everything is known, you can find out the depletion width. Right? So if you recall, I had given an example, where a few slides back, if you remember, I had solved a problem few slides back. I'm not able to recall where I had solved a numerical. Yeah, it's here. I had solved a numerical, and the p side is 10 to the power 17 doped, and the n side is 10 to the power 16 doped, and the built-in potential came out to be 0.76 volt. So if I take the same expression here, right? If I take the same expression here now, and I try to do the depletion width, so what? I will basically take the same thing. So this is your Fermi level, conduction band, valence band. This is your x equal to 0. This is your depletion. This is your built-in potential. Okay. This is n-type doping is 10 to the power 16. P-type doping is say 10 to the power 17. Okay, per centimeter cube. It's always in per unit volume, of course. So then your built-in potential, it came out to be around 0.76 volt. So then you, for finding out what is the depletion, this total depletion W, you just have to do W equal to square root 2 into epsilon, which is 8.854 into 10 to the power minus 14 farad per centimeter. You should be very careful about the units. Okay, divided by Q, which is 1.6 into 10 to the power minus 19 coulomb, into your epsilon of silicon is 11.7 into built-in voltage Q Vbi, which is 0.76, this, into 1 by doping, 1 by 10 to the power 17 by 1 by 10 to the power 16. So if you do this, you will find out the value of W, and it can be a few hundred nanometer, depends on whatever, right? So of course, as your doping is lighter, your depletion width is larger. If your doping is narrower, very higher, then your depletion width is narrower, okay, and your built-in potential is higher, right? So this is what, now once you know the depletion, suppose the depletion comes out to be 200 nanometer. I'm just giving an example. Then how will you find out the depletion and n side? Oh, that you find out by this relation, right? This relation, which is depletion on the n side is total depletion into Na plus Nd. So if this is 200 nanometer, then it will be 200 is total depletion. Doping on p side is 10 to the power 17, and this will be 10 to the power 17 plus 10 to the power 16. So you find out this will be 200 into 10 to the power 17 by 11 into 10 to the power 6, 1.1 into 10 to the power 17. So this will be 200 by 1.1, that whatever that value is will be that nanometer depletion on the N side. So I told you if the p type is 10 times higher doping, then the depletion on the N side will be 10 times higher. That's what basically it means. Okay. So we have now understood the potential on both sides. How is the potential dropping and total voltage we have related to the depletion width, and I told you that your field, electric field, if you recall, this is Wn, this is minus Wp. Okay, the field actually is maximum here. It goes like that. This maximum field is, remember, Q Nd Wn by epsilon naught epsilon s, which is also equal to Q N A Wp epsilon naught epsilon s. The whole analysis that we have done till now assumes complete depletion approximation, which means this is x equal to 0. For example, if I draw the charge on Wn, you have positively charged ionized cores, and on the other side you have minus Wp, so you have negatively charged acceptor ions. The assumption, the depletion approximation tells us that there is absolutely no mobile carrier within this and within this. So this is your total depletion. So there is absolutely no mobile carrier here. Everything is ionized immobile charges, and we solve the Poisson equation here. We get the field as we have discussed. We also get the potential profile. So we are good to set up the the field and the potential energy profile. So now we basically know the static conditions. Okay, there will be many numerical problems to find out. For example, what is the maximum field? Values will be given to you. What is the depletion width? W, again values will be given to you, or you are given the depletion width, but you are not given the doping, and vice versa. So there could be many numerical problems that you are asked to solve. So this is about basically about whatever we have learned till now is about p-n junction in equilibrium or static conditions. There is no voltage applied. There is essentially no bias, no light shining. So essentially it's p-n junction in equilibrium. There is no current flowing. Okay, there is absolutely no current flowing. So that's good. Now we are good to move ahead with the next concept here. Okay, we'll go to p-n junction in bias, but before that, let's stop for a minute and think about it. Realistically about different kind of semiconductors. So I told you that if you have say silicon, the band gap is 1.1 eV. Suppose you have gallium nitride. This is another semiconductor whose band gap is 3.4 eV. So silicon, this is p-n junction, right? So this is Fermi level, and this is your p-n junction like this. Sorry, your p-n junction like this. Okay, for gallium nitride, the band gap is large, so like that. So of course the built-in potential QVBI, okay, QVBI, I had mentioned it, is equal to KT by Q ln of Na Nd by Ni square. So if this doping is same, then Ni for gallium nitride is much lower. So that's why your built-in potential, this is much higher. This built-in potential scales roughly as the band gap. So if your band gap is large, then the built-in potential also will be large. Please keep that in mind. Okay, and that's very important, as you can look at the dependence on temperature. If you increase the temperature, what will happen? Because this will, if you increase the temperature, then this will increase. Ni square also will actually increase with temperature, so this will blow up, which means the overall quantity will have to shrink, right? So there are many things like this that we have to be careful about while you do device problems. And also there could be another thing is that when you increase the doping, what happens? Suppose I take only silicon. I have two silicon p-n junctions. A sample 1 has n p-type doping as 10 to the power 15, n-type doping also as 10 to the power 15, say same type. I have a sample 2 where p-type doping is 10 to the power 18 and n-type doping also is 10 to the power 18, which is very high. Both of them are equal, but they are very, very high doping here, and there is very light doping here. So what will happen now? The built-in potential for this sample will be much lower because your Na-Nd product is much lower. The built-in potential here will be much higher, compared to that, much higher as in like higher because your product is higher, right. Now which will what is the limit to having a, what is the largest built-in potential one can have? The largest built-in potential one can have is the band gap of the semiconductor, right. So no matter how high you dope, you cannot exceed the band gap of the semiconductor, right, because if you look at the band diagram of p-n junction again, right. So this is your suppose Fermi level and this is your conduction band, this is your valence band. This maximum that you can get is actually the band gap, and you will get that when when you have such high doping that your Fermi level on both sides touch the valence and conduction band. Suppose this is your valence band, but the Fermi level is on the p type, on the p side the Fermi level is so highly doped that Fermi level is touching almost the valence band. Similarly on the n side Fermi level is touching, this is Fermi level which is also touching the conduction band on this side. The Fermi level is also touching the valence band on the p side. On the n side Fermi level is also touching the conduction band, and then it's going like this, right. This is the largest built-in potential you can have. You see the built-in potential is equal to band gap, because this value is actually this value which is the band gap, because this is your EC, this is your EV. So in the limit that your Fermi level is touching the conduction band, the Fermi level is touching the valence band, which means the doping is super high, very high. In that limit your built-in potential will be equal to the band gap. Of course when your doping is very high, if your doping is super high, Na and Nd are 10 to the power 18, right, then you remember the depletion with 2 epsilon by Q Vbi 1 by Na plus 1 by Nd. If this Na and Nd is 10 to the power 15, then this is very large. If this Na and Nd are 10 to the power 18, then this will be very narrow, which means this depletion will be very narrow. So it will be very sharp. So actually how it will look like, it will be very narrow junction, because the depletion will be very low because your doping is very high. So your built-in potential and your depletion go inversely as the doping, no. So what will happen is that if this is your Fermi level, then your conduction band valence, it will have a very sharp depletion like this, okay. It will have a very sharp depletion, like the depletion, this is the depletion, the total depletion is this, okay. The total depletion is this is your x equal to 0, because the doping on both sides is same 10 to the power 18, 10 to the power 18. It will be the same doping on both, same depletion on both sides, but it will be very narrow. It can be even 10 nanometer or 20 nanometer or so on. There is a lot of holes, there is a lot of electrons, okay. If this is very narrow, then the depletion essentially is very narrow. So electrons and holes can even tunnel, that will come later. There is tunnel diode you can make, tunneling diode you can make, because it is very narrow. So electrons and holes can tunnel. If you don't know what is tunnel, this is a quantum mechanical process where electron can or hole can, for example, move across a barrier, unlike in real life. So if you have a wall, then you have a ball, it will not be able to cross the ball, but in quantum mechanics an electron may be able to cross the wall. Actually when I say wall, it's not the wall made of brick or stone, this is the wall of potential energy, okay. But let's not talk about that. So anyways, the depletion will be very narrow if you have a doping is very high. So this is 10 to the power 18, this is 10 to the power 18, doping is very high, the depletion is very narrow, and the largest built-in potential you can have is the band gap. Beyond that, there's no depletion. This is the largest depletion region you can have basically, okay. So we shall end the class today. We have finished up static conditions of p-n junction. We have started with the relation between the Poisson equation and tried to establish the relation between the field, the depletion region and the built-in potential, what is the maximum field, the potential drop on each side. We solved some numericals, some simple examples, but there can be a variety of numericals. Different parameters can be given, because we have established the mathematical relation between the depletion width and the built-in potential. With higher doping, depletion width will come down and built-in potential will go up, okay. Please remember that. So static conditions of p-n junctions are now thorough. We have now full control on that. What we will do in the next class is we will start with application of bias. Once we apply voltage to p-n junction, what will happen, right? What will happen? Current will flow. How do you understand that current flow? Now that will take some time. So we will start that from the next class, okay. Thank you.